All right, we're going to do a mic test first. And then there'll be some delay. All right, we're going to do a mic test first. All right, seems like the test worked. So what I've got is 5 problems listed here, 4 of which are in your assignment for this week, and this one will probably be in later. So I'm going to go from right to left. If I don't have time to get here, that's okay. That could be next week's. Two ways you can look at this one. One is with the instant center, and this one will give you some interesting pause for thought. Let's just say that this was, oops, hang on. Let's see what this one looks like. Yeah, that's good enough. Let's say that's just, okay, so we got measurements here and here. Just to make my life simple, let's just say that's 1. If this is rotating this way, the velocity will come down like this. Over here, the velocity is either going to go this way or this way. You really don't need to know which particular way at this point. And then what you do is you come in and you draw your perpendiculars. Well, let's choose this color. You draw a perpendicular line to the known velocity and you extend it either direction. Then you go over, you draw a perpendicular line to another velocity, and you look for where they cross. They actually cross, ooh, how wild. They actually cross right there. So they're actually crossing right at that point. So believe it or not, it doesn't make sense, but it is really true. It appears like this link is rotating about this instant center at this instant. Therefore, if that were 1, this would be, this would be V is equal to omega R, or 1 times 0.6, y 0.6, because it is on this link. So what we're doing is we're using our knowledge of link AB to determine velocity of B, and it ends up being 0.6. So that's the velocity here, equals 0.6. Now, if we're looking at this link now, it appears to be rotating about this point, and it's omega. Okay, so V of B is equal to omega of BC times the distance, or the R, from B to the instant center, and that happens to be 1.2. The velocity here from this location, from right here, from what we determined on this last link, that is 0.6. So that means the only way you can get that to work out is if omega BC were equal to 0.5. So that's how you do that with instant centers. I may come back and do this one with the equation sets. You'll see something interesting there. But first I want to go ahead and address this one. This one's interesting. Okay. We're going to add complexity here. Let's say this velocity, he's obviously drawn it right here, but I'm going to draw it in the center right here, and I'm going to say this is the velocity magnitude. Let's say we did it to scale, so this is the velocity here. Now, if B is, say, if B is fixed, then this point right here doesn't have a velocity, and so all these points out here, which are perpendicular, have a velocity profile like so. Okay, let me see if I can do a reasonable job. So the velocity all the way out on this gear tip here, the velocity here is this, velocity here is obviously that, so on and so forth. Now if we want to know the velocity of point A, okay, so here's the other thing. I'm just going to say this. Oh, he gives us that. Here is the distance from this point to that point. So let's say he just happened to give us this being 1. Okay, so velocity at the O is equal to omega of the wheel times r from the instant center to the O. In this case, the velocity might be 1. I'm just saying it is. Omega is the unknown, and that is your 0.3. So I should have come up with a different value for there, but that's okay. Omega is equal to 1 divided by 0.3. Now that you have that omega of this whole wheel, let's assume for a moment you're interested in the velocity at point A. So you draw yourself a line out here to point A, and then what you do is you draw the vector of, so here's your velocity vector, right? And you're sitting here looking at this. Oops. Yeah, let's go ahead and put that back on there. Let's say you could figure out this distance. Can you actually? Well, yeah, because if you look at it, okay, let's see, how can I do this? I think I could do it this way. If I were to look at this, and then go and grab that, move it over here, that would be a triangle in which, if you really look at this close, this top distance would be, okay, hang on, hit the escape key. This top distance would be 0.6. This would be 0.3. This would be the square root of 0.6 squared plus 0.3 squared. That would be the distance from here to here. Then if you want to know the velocity at this point, velocity is equal to the omega that we got from before times the r, or the distance that is right there, which would be equal to 1 divided by 0.3 times the square root of that 0.6 squared plus 0.3 squared, and you just calculate that, and that'll be the velocity there. Let's take a case in which slightly different. Let's assume for a moment, okay, that the velocity okay, hang on. Okay, let's assume this is as large as I can zoom it in. Let's assume for a moment the velocity is to the right and it's this magnitude. But let's assume we're dragging this rack to the right with a velocity. And let's assume for a moment that we're dragging it with a velocity which is slightly larger than this. Okay, so there you go. Now, let's take a vertical line. That happens to be the reason it's vertical, the reason you're interested in it. It's perpendicular to those. And then what we do is we just simply draw a line like this. So this particular point becomes the instant center. This actual point is moving backwards. All the rest of these points are moving to the right. The largest velocity is this one. Let's take another case. Okay. Okay, I don't know what happened here. Okay. All right, let's take this third case here. Here's a third case. Let's assume velocity is to the right. Say it's to scale. This time we drag the rack back to the left. So it's going to the left with the speed. Okay, technically, although you probably don't have to, but here's my lines that are perpendicular. Okay. They both, that single line is coalescent, meaning the perpendicular here and the perpendicular here, there's just one single line, what appears to be one single line. Now, again, let's draw tip to tip. Okay, in this particular case, here's your velocities. Here's your velocity profile, so to speak. Going really fast at the top. Kind of somewhat fast. Instant center. That's the point that has a zero velocity. And the bottom of the wheel. Going to the left there. And that's pretty much it. Now, let's try a third one. Okay. This is a very bizarre one. Okay, let's see if I can find out where. Okay. Let's say we didn't know the rack. This would be a very odd problem, okay? Let's say we didn't know the rack speed. But for some bizarre, weird reason, somebody was measuring like the and had the velocity, magnitude, or even just the direction right here. So let's say he put a spot on it, measured it, and he said, here's your velocity direction. Then the question is, what is the rack speed? Is it going this way? Is it going that way? Actually, not too hard. Here's your perpendicular. Here's your perpendicular. There's your instant center. Here. Now that your instant center, you know your spot has to go through here. And suddenly, you have your speed of your rack. I can't zoom in any closer than this, but there's the speed of your rack. So it's going to the left, and it's going a small velocity. If in fact that instant center touched the rack exactly where they intersected, then the rack is sitting still. If in fact, let's assume for a moment that the thing is tilting like so. Okay, let's assume it's going like so. Draw your perpendicular. There's kind of art here. There's your perpendicular. Here's your perpendicular here. Looks like the instant center is right there, which now, if you go right here where these two gears are touching, so to speak, coming back to the left, this in fact is the velocity of the rack, or velocity of B. So hopefully that explains things moderately well, I hope. So there are multiple cases there. Let's take a look at this one now. Okay. I know this is spinning this way with a number here. Let's just make a number equal to 1. I'm sure I'm using 1 a lot, but that's okay. That means this point is spinning or going back to your left, and its velocity there is equal to omega r, or 1 times that 0.2, or 0.2. Now, I don't know that this is technically 30 degrees. Actually, it looks like it actually is 30 degrees. So it is velocity. Technically, you don't need to know the direction. It could be this way, could be that way. Now, I need to find the perpendicular, the point, put it right on the peg, the point that is common to both bodies. And if I zoom out, I see that. Now, okay, let's zoom in and recognize that what we did was we found a perpendicular like so. And then we found a perpendicular like this. Okay, well, here. Now, and in fact, here's your instant center up here. And it appears like this thing is rotating that way. Otherwise, the reason you can make that assumption is because the velocity down here is to the left. If you wanted to do a profile like what we did previously, you would do something like this. Okay, now I'm trying my best here. And I would draw a line like that. And although these points are not on the body, if there was an object there, these would be the velocities. Now, the thing is you need to know the distance here from here to here. I would call it distance B instant center. Once you have that distance, then you can realize, well, velocity at this point, which is equal to 0.2, is equal to omega of BC times the distance from B, that was to the instant center. That would be this distance right here. And so once you found that distance, you could find that omega right there. The next thing you want to do is find the distance from here to there. Distance from C to the instant center. Then if you want to, you can find the velocity of this spot. Now, you have to realize from here, I figured out that the rotation is in fact this way. If it is this way, then actually your velocity is most definitely like this. And this velocity is nothing more than omega BC times the distance from C to the instant center, this distance right here. And that's pretty much it. Like I said, let me come back and do these the other way as well. Okay, let's look at this one. Okay. Here, I'm going to try my best to assume, hopefully rather reasonably, and it seems like rather reasonably, that the velocity at this point is going in that direction. And I know for sure that this velocity either goes that way or the other way. So now my goal is to find the perpendiculars. Here's the perpendicular to 1. Okay, hang on. Okay, so there's my perpendicular to one of them. Meaning, I do this. Okay, here's my perpendicular to the other. And this, in fact, is my instant center. Now, we have to understand that although this is 0.2 for the sake of our triangle, which I'm going to draw now in this purple, I'm going to come down here, and then I'm going to go over here. There's my triangle. I'm going to select that triangle, move it off to the side. I'm going to make use of a couple facts. First fact, that's 30 degrees. Therefore, this is 30 degrees. Second fact is that's the 0.4. So with that and that, the other two, I can actually find all of my distances. Mainly, let's see if I can move the ruler out of the way for the moment. So cosine of 30 is equal to, we're going to call this B distance, B instant center. Okay, so it's going to be 0.4 over distance B instant center. We're going to call this the distance from C. Okay, remember this is C. This is B. This is instant center. Distance from C to the instant center. And sine 30 is 0.4 over distance from C to the instant center. So from that, you can find this and you can find that. Now that you have this, if you were given this value, you have that. So you can find the velocity here. V is equal to omega AB times your 0.2. Now, what's interesting is not only is it connected to, B is connected to this body, rigid link, and it's also connected to that rigid link. As a result, you could view this as a big, huge triangle that is, in fact, rotating like so. This means if it's rotating like so, the velocity here is to the right. Velocity there, of course, we figured out. We should have figured this one out because someone would have given us this. And what we would be finding is omega of link BC. Now, if we want to know the velocity of C down here, that's actually not too particularly hard. That velocity is equal to the omega BC, which existed right here, times the distance C to the instant center, where that distance C to the instant center is that, which is the same thing as that distance. That's pretty much it. Okay, I did all four, kind of laid out all four. Let me now kind of go back through these in a way that is consistent with the vector equations. And I'll start from the left, go back to the right. So if I have velocity here, if I have the velocity of B is equal to velocity of B relative to A plus the velocity of A, then I am on link AB. I'm on that link. Since that is nothing more than omega AB, which is that cross RBA plus velocity A, which in fact, since this is attached to the ground, that's going to be 0. And you get velocity B. You have to maintain your sign conventions. It's a good idea to learn those anyway. Plus rotation. Okay, so this is a minus. So it's up to you. I, J, K. But if he gave you that number and gave you its direction, say he gave you this value. Well, I'll just go ahead and do this. Say minus 10. So say he said that omega AB is equal to 10. So why is it minus 10? Because this is the direction it is. This is by definition the direction of a positive rotation. Next, I need a vector. This vector, this is the only difficulty you have here, and it's not that difficult. You need a vector, which basically starts at A, goes to B. Okay. So R, drawn to B, originating from A, is equal to 0.2 cosine 30 I plus 0.2 sine of 30 J. So 0.2 cosine 30, there's my shorthand, and 0.2 sine of 30, and then 0. So if you do the cofactor expansion, you'll get this minus J, and you'll get this equals to that times that minus that times that, which is basically 10. Let's say, well, let's just do it this way. I'll write them out now. Plus, minus, a minus, a minus. Okay. And that's that. Okay, to check yourself, you can take this, multiply times this one, add it to this one, multiplied times that one. What you should find is that basically they cancel each other out, and you should get a 0 by definition. Okay. So there's your velocity B. Now you can write your link from velocity of, say, C is equal to velocity of C relative to B plus velocity of B, implying that the fact that you've got a C and a B on the same length. So there's your link CB. Here's your link AB. C and B sit right there. Here they are. So pretty simple. velocity of C is equal to this, which is omega BC, which we don't know, cross R CB plus velocity of B. These should all have been vectors, which in fact this can eventually be put in there. A vector originating B, ending at C, originating at B, ending at C is a pretty simple vector. Only has a component to the right, 0.4. So 0.4, 0, and 0, I, J, and K, 0, omega BC, plus velocity of B, which I can write that down. And you know what? Instead of just keep writing this 10, I'm just going to write it as a omega AB, whatever's given, 0.2 sine of 30I minus 0.2 cosine of 30J. Where am I getting that from? I'm basically taking this and writing it right here, replacing back my omega with 10 ABC, just in case there's another value besides 10. Okay, now this should say BC, and if we go in and take a look at this point, you're only going to have a component in the one direction. Okay, hang on. Sorry. Okay. So, if you do a cofactor expansion about I and look at that determinant, you get nothing. If you go do a cofactor expansion about J and look at this determinant, it's the only one you'll get something from. So I'm just going to write it down. Plus all this here. And the magic of this stuff is that I can just simply put it right there. Okay, so I can basically, that times that, minus that times that, but there's already a minus. So I get, okay, come on. What's going on here? Okay, I got frozen for some reason. Okay, there we go. So I get 4 mega BCJ. I am confused, but here we go. Now, one of the things about velocity at C is velocity C only goes to the right or left because it's confined to be attached to this pin. So I'm just going to basically list it as being VCI. I'm going to list it as going to the right, plus, and the magic of the copy pin, copy, paste, and here we go. So here's, I'm going to do this. I think This is a way to do it. And we'll just pick that color. Did it not work? Oh, shoot. It's not working. Well, here. Now, let's see if I can do this. Try it now. Yes. Now, so there's our final equation. We can pull out the I components, which will have VC is equal to, I don't have anything over there except that. Make A, B, 0.2 sine of 30. And then I have my J equation, which tells me 0 is equal to 4 omega BC minus omega AB times 0.2 cosine of 30. Now we have to remember back that, in fact, this term would have been given, and so from that, I don't know, the upper equation, you can get your velocity. From the lower equation, you get the omega BC. So that's the approach from the vector equations. Both should come up with the exact same answers. You can sort of check this out, but okay, let's see. Yeah, I'll leave it to you to check out, because you can have two ways to work this. The only one other that might be interesting with regard in this regard is this one, and we're kind of cramped for space there, but we can do it. We just may have to move it. So so here's what we'll end up doing. So velocity, remember A, okay, so I'll say velocity of B is equal to velocity of B relative to A plus velocity of A. I'm on that link. That's AB. Turns out A is fixed. I can do also the link BC. Velocity of C is equal to velocity of C relative to B plus velocity of B, which actually I would solve this one and then put this in there. But the velocity of C is confounded to go off to the right. So it would be VC cosine 30I plus VC sine of 30J. If it didn't go up and to the right and it went down to the left, the solution would come up with a minus number here and a minus number here, which is the same two numbers. Okay, so you look at this one back here, you have to maintain your two common features there. Okay, so here's my X, here's my Y, and there's my plus omega. So excuse me, sorry. So I'm going to end up with J and K I should move this down because this term would become omega AB, the vector, with the sign associated like that, cross RBA. Now, I'm just going to say AB. Then the R, believe it or not, is just nothing to the right. The vector is a vector that goes straight up, 0.2 and 0, plus nothing because point A is pinned to the ground. So you'll get velocity of B being nothing more than, okay, now if I do a cofactor expansion with this and look at this part, the determinant in that, I don't get anything, but I do with the I. 0.2 omega AB 0, which equals to plus and then minus 0.2 omega AB I, and that's the velocity of B. Does that make sense? If in fact the wheel is rotating this way, which these two directions are both the same way, the velocity runs back to the left, and that's consistent with the minus sign here. Now, what you're doing on the second link is this omega BC. I don't know what omega BC is yet. R C to B plus velocity of B. So what I'm doing is I'm now on the second link. Now, what's interesting here, and I can use the magic of the copy, select and copy, and I'll say this is nothing more than I, J, and K, and 0, 0, omega BC, don't know what it is. Now a vector from that starts at B, ends at C. Starts at B, ends at C. It's nothing more than 0.8 I. 0.8, 0, and 0. Plus, what do I put down for VB? Well, here's what I put down for VB. Magic of the copy and paste again. Copy, and we'll see about placing it somewhere. Say right there. Here, we'll do that. And then I can zoom in and erase these two. There you go. So this, in fact, is this. So again, this thing, okay, so if I take the I cofactor expansion and look at the determinant right there, what do I get? I get 0. But if I take the J cofactor expansion and then I look at this and this part of the matrix, I get something different. Minus J times 0 omega BC 0.8 and 0 minus 0.2 omega AB I equals to that. Okay, now here's your deal. Break it into components. Okay, I guess I should do this first. This times this, minus that times that. Already has a minus. Becomes 0.8 omega BC J minus 0.2 omega AB I. And so this. So what you get is, well, first I need to break it into components. VC cosine 30 equal to minus 0.2 omega AB. That's for the I component here and the I component there. The J component should give you this and this. VC sine of 30 is equal to 0.8 omega BC. Now, we have to remember back how this thing started. More than likely, somebody gave you this number, say 10 or 5 or 2 or 1 or something. So in other words, omega AB, the driving frequency, is going to be given. So this means that what's going to be given, this. From that being given, you can solve for this. Whatever your solution is, which just happens to be taking the cosine and slipping it under on the right side, you put that in here, and you can find the omega BC out of that. And so we'll go ahead and draw this to a close and say we're done.